wave function somehow encapsulates the information that we have about the state of the particle. So, for example, in the simple case of a free particle, say a lonely electron moving without being subject to external forces, and this electron has a wave function associated with it, which encodes the state, kinematic, for example, state of the particle. In classical physics, this is equivalent to giving the positions and velocities of the particle. And in classical physics, we have equations which tell us how a particle evolves given a certain state at a certain time. What's the equivalent in quantum mechanics of this evolution function?
So the equivalent, it's of course several actually in practice. So of course the point that you're making is that you have this wave function, and this wave function encodes the information, and this is exactly a good way to put it. And this is one of the few things that all the interpretation agree on, the fact that the wave function encodes the information. And then some interpretations say that it encodes something more than the information, not that just keep it like this. Because, of course, it has to encode the information, otherwise I wouldn't be able to extract any property of this particle, and I wouldn't be able to compare it to experiment. Now, you say that in the free case, if an electron is moving without being subject to any potential, any force, external force, like the nucleus in my example, it will have a wave function. That in this case will be a what is called a planar wave function, so a simple trigonometric function, is a sinus, basically, and goes ups and down in all the space. And now your question was, what defines the time evolution of this particle moving in free space? So in classical physics, I will have the particle that is a point described by position and momentum, and I will have the evolution of position and momentum in few different relations according to what type of position and momentum there is. If the position and momentum, or if the momentum is small enough, so it's a classical particle moving classically, then the relation will be kinematic. And the corresponding, in the quantum mechanics case, it's the Shrödinger equation, if the velocities are small enough. However, if the velocities get large enough, what I will have, if the momenta get large enough, what I will have is a relativistic time evolution. And this has both a correspondence in Schrödinger, in classical mechanics with the relativistic time evolution and Lorentz invariance, and in the quantum relativistic interpretation, that in the case of the electron will be given by the Dirac equation. Now, the important thing here that I want to stress, that is not stressed often enough, is that actually classical mechanics and quantum mechanics have very, very similar formulations. It's just that they are not used very often to describe simple motions. So in classical mechanics, if I want to describe the movement of a particle moving in the vacuum, then I use the kinematics. This is in this case, it's a simple uniform motion, and it's described with the simple equation that I studied in high school, the relation between velocity and time and space. So that's the usual description that you use for such a simple particle. However, you can use a more complicated description that is very, very useful in the case of more complicated systems. So for example, if I have a particle that instead of moving in the vacuum, is rolling around the ball. So if I have a particle rolling around the ball, this is a deceptively complicated problem, because you have that the forces live in 3 dimensions, because the ball and the gravity pulls it down, but the ball has a 3-dimensional, as a surface defined in 3 dimensions, but it's a surface, so the ball is linked to this 2-dimensional surface in 3 dimensions with the force. So this very quickly becomes a complicated problem that is solved in what is called Hamiltonian mechanics. And exactly the same type of mechanics is used to describe quantum mechanics. So also in quantum mechanics, you have an Hamiltonian evolution of the system, and this is exactly the same. We can say that it is exactly the same as in classical mechanics, at least the description of the relations between quantities, between position and momentum, between energy and time. There are, of course, there is one key differences, which is what everybody knows as Heisenberg uncertainty principle. But that also has a classical correspondence. So it's not that quantum mechanics is dropped from the sky and it's a completely different world. In some sense it is, and in the philosophical sense maybe it is. But in the physical and technical sense, the quantum mechanics was on purpose developed so to be just a continuation of what was coming before, and in this case was the most sophisticated way that we had to describe classical particles. That was Hamiltonian mechanics in case of classical particles, or Lagrangian mechanics in case of both classical and relativistic particles. And the same can be said in quantum mechanics. You have an Hamiltonian evolution or a Lagrangian evolution, and there is really a one-to-one correspondence between classical and quantum mechanics in the formalism. And then the results differ, because in classical mechanics you are evolving a point-like particles, or in any case a particle which has a definite shape, while in quantum mechanics you are evolving a wave function. So you are evolving a distribution. So this is the true difference. It's not the evolution itself, even though of course it plays a role, and if you want to describe it in the simplest way possible, then the two evolutions need to be radically different, because the solution to the Shrödinger equation will need to give you the wave function in and of itself. But if you want to describe the time evolution in a very similar way with a very similar formalism, you just set up an Hamiltonian mechanics and you're done. It's if it is quantum, you will evolve a point or a ball, and if it is classical, you will evolve a point or a ball, and if it's quantum, you will evolve a wave function with a certain shape. So that's also part of the beauty of mathematics, that with you set up an architecture, a conceptual architecture, and then you can use it to describe different things. That's the power.